joined with the graduate school workshop, and I'm very happy to introduce Scott Wolpert. And his title is Prime Geodesics Theory.
Thank you. So it's a pleasure to be back in Stony Brook. Yesterday was beautiful weather. I'll overlook the management of the weather today, but yesterday was certainly beautiful. So I'm going to speak about a theorem and approach of Mariam Mirzakhani to counting simple closed geodesics on hyperbolic surfaces. So let me start just with the background or the context. To remind you, there's the much older result that the count by length of closed geodesics on a hyperbolic surface, so the number of geodesics of length at most L is e to the L over L. So it's a very large number. Then in 2008, Mariam gave there was a trio of papers which were interconnected, and one of the papers has this beautiful formula for counting simple closed geodesics, and actually for counting a little more than simple closed geodesics, for counting multi-curves. So a multi-curve is a union of disjoint simple closed geodesics. In fact, in the way we're going to work with them, we want this to be with weights. So it's going to be a collection of curves with weights on them, and this is going to be part of the counting recipe. All right. And so one of the reasons I personally like her approach is it involves many of my favorite pieces of Teichmuir theory and Thurston theory. So this is, in fact, a good way to see how different parts of the Thurston theory and Teichmuir theory and Mariam's contributions and some algebraic geometry all fit together at the same time. So when we have a multi-curve, then its length will be the weighted sum of lengths of the pieces. And we start off thinking about this in the topology of this situation. So we introduce the mapping class group. So if we have a Riemann surface R, then the mapping class group is the quotient of orientation preserving homeomorphisms modulo those homotopic to the identity. And part of her approach involves thinking about what's going on with the collection of all multi-curves. And so she's particularly interested in the orbit of a multi-curve under the mapping class group. And then and we're going to see there's a space, I guess on the next page, that this is the orbit that we're viewing the orbit in, but let me postpone that a little bit. And so her counting function's the following. We have a multi-curve, and then we consider its orbit by the mapping class group, and then certainly for each element, we've fixed a Riemann surface R, and then for each element in the orbit, we can take the sum of the lengths, and we're always using geodesics. So when we take a curve and we act on it by homeomorphism, the way we want to think about that is that we get a free homotopy class, and we use the geodesic in that free homotopy class and take its length. Are they what? Integers? No, they can. At this point, I'm going to say they're rational numbers. So in general, they're real numbers, but in the next minute or 2 minutes, they're going to be rational numbers, which actually she doesn't need, but at least to explain the proof at first, we're going to assume they're rational. All right, so here's her result. And so for a rational multi-curve, then the number of rational multi-curves in this mapping class group orbit of length at most L is asymptotic to, so actually let me start over here first. So we're looking at length L, it's L to 6 this power where G is the genus, and N, the surface might have punctures or boundaries, and N is the number of punctures or boundaries. All right, so there's this, which is very surprising at first. This was not a new result. This had already been detected in a paper of Riven and a co-author whose name I forget right now. But so first notice just this dramatic change, and that is for all geodesics it was exponential growth, and here we're now down to power growth, polynomial growth. All right. Now, these constants are very interesting, and we're going to see where they come from. But for now, this is the Thurston volume, which I'll be explaining what it is, of something called the unit ball in the space of measured laminations. And I'll explain what that is in the next page, give you at least an immediate definition. This, of all things, and I think it's very beautiful, this number involves characteristic numbers on the moduli space of Riemann surfaces of two standard line bundles or two standard divisor classes. So at least to me this was really quite dramatic when you see this, because you're counting curves on a surface and you wonder, how did you get to characteristic classes on the moduli space? I mean, this is quite something.
Sorry, what's topologically equivalent mean?
Here it means that there's a homeomorphism that takes one configuration to the other. So this, actually, the way I've written this sentence, it's kind of a tautology. Or I'll say it naively, meaning giving the same picture.
Look at the images of all these curves, right?
Yes.
Under the mapping class.
Yes. Yes. All right. So, yes. So this C of gamma, again, is going to be intersection numbers on the moduli space of Riemann surfaces. We'll come to that later. This BGM is just, in fact, the integral over the moduli space of the Thurston volume of this unit ball, which we'll come to later, integrated against the Weil-Petersen volume element. So this, at least on the face of it, gives you the definition of the quantities in the statement of the theorem. All right, so from here up, so let me just say a little here, and then I'm going to proceed. So there are a number of follow-up works to this. There's one by Mirzakhani at preprint that never made it into print. And then there's two papers, at least, by Erlandson and Soto. And there's also work of Rafi and Soto. And these papers start to cover curves which have a fixed amount of self-intersection. So these works already are moving into beyond simple closed curves. These papers, I'm going to say, take a more direct approach to the counting, because you're going to see as I go through this present argument of Merriam's, hers is, it uses a lot of high-level structure, and in some sense thinking of the moduli space like a locally symmetric space, whereas these, in the other authors, I'm going to say, and even her later work, they're looking more right at the curves and figuring out some scheme to actually count these curves on the surface. So, which is certainly more nitty-gritty, and there are two different certainly two different styles of approaching the question. All right, now I was going to announce or talk also about two corollaries which I've been working on for some time, but about 2 weeks ago I realized I don't have the proof. So they've been changed back to conjectures. So I'm going to tell you two conjectures which should be which should follow readily from her theorem, but they don't. And I'll even say a little why it's not so easy. All right, so let me now describe those two conjectures or two related countings you might do. So for one, in a lot of questions when you're working on Riemann surfaces, you're interested in what's called a Pants decomposition. So this is choosing 3g minus 3 plus n simple closed curves to cut the surface up into a union of three-hold spheres. And both for topological reasons and geometric reasons, this can be very convenient and useful tool to analyze what's going on either with the geometry or topology. Now, so her...
Sorry, stop.
Yeah.
The n refers to something with the point, the punctures, right?
Yes, punctures.
So I can see what you do geodesics for the pants, but what do you do with the punctures?
So pants can also have zero length boundaries. So you could have a pair of pants which has one or two boundaries which actually are zero length, meaning they're actually cusps.
There's one there.
Yes, so here's one, such a pair of pants.
Somebody with small waist.
Right. Someone who went too far. All right. Now, her result does cover, because even in this picture, this is a multi-curve, but if we look back in the other page, we see in her result, she adds up the lengths. So she's only looking at the sum of the lengths. And in fact, in a number of geometric settings, it's actually, you want to control the individual lengths. And her method, certainly on the face of it, only controls the weighted sum of the lengths. And so something you would want to know, and actually, well, something you would want to know is the following. Suppose you gave intervals in the real line, and you asked for a pants decomposition, and you asked that each one of these seams had its length in a prescribed interval. So looking at her formula, and I'm going to say for multiple reasons, it seems to be clear what the result should be. The result should be that counting such pants decompositions where the lengths are prescribed to be in intervals, scalings of intervals, it should have the same type formula. And in fact, we know what the behavior of the weights should be because these endpoints of intervals. It should be the product of the difference of the squares of these lengths. And in some sense, we'll see that later. And then certainly the same L to the 6G minus 6 plus 2N. And we even know what characteristic class should sit here. But so far, at least the proof's been eluding me. Let me describe another question one's interested in that's actually closely related to this question. So another question is to do the following, and that is if you have a cusp, so that would run off to infinity, then what you could do is you could look at curves that start in simple curves that start in a cusp, come into the body of the surface, and run back out to the cusp. And you could ask to count their lengths. Now, their lengths are infinite, but there's a obvious way to standardly truncate that geodesic and renormalize their length. And that is, you could pick your favorite small integer, like 1. And what you could do is you could take the length 1 horocycle around the cusp, and then you could ask what's the length of the segment of such a curve outside of the horocycle. And that would certainly be a reduced length. And we would like to count the spectrum of reduced lengths. And in fact, at least at the outset, we would expect it should follow the same asymptotic type formula as in her theorem. And so the first thing to check is to do some hyperbolic trigonometry, and you ask yourself, well, so let me go back to this picture again. If I have this geometric situation, then what is an expression for this reduced length? Well, first of all, if I have such a curve like this, it actually already determines a pair of pants, because here's a simple closed geodesic, a simple closed loop, say on the left side, and then there's a simple closed loop on the right side by following part of this geodesic and part of the Horus cycle. And so those loops, then they're geodesics in those free homotopy classes, so that would be here and here. And so in fact, just having this segment here already determines a pair of pants. So a simple exercise is to ask the following. Well, on that pair of pants, what's the relation between that reduced length and the length of these two boundaries of the pair of pants? All right, so that, in fact, is a straightforward exercise in hyperbolic trigonometry. And the answer is very simple. And the answer is this, that this reduced length of that segment, it's equal to the max of the length of the two boundaries plus a uniformly bounded term. So asking what the length of the what this reduced length is, it's the same as doing the following. Considering that pair of pants, and then looking at the two boundaries and asking what's the max of the length of the two boundaries. All right. So again, this does not immediately fit into Miriam's setup because in her setup, when she has multiple curves, she's always adding their lengths together and considering only the sum, not the individual entries. All right. So nevertheless, looking at her final formula and parts of her arguments, there's a straightforward presumption of what the formula should be in the count. And it should be, the formula should look like this. So again, they're quantities we recognize. It would be characteristic classes we know, and that's what we expect the count to be. All right. And it doesn't matter where we truncate, because where we truncate only changes our length by adding on a fixed constant. And we're doing an asymptotic count, and so this is not going to change the asymptotic count.
Were you counting?
So I'm counting these reduced lengths. So I would do the following. So you would take one of those curves in the picture. You'd let the mapping class group act on this loop, this infinite loop. And then you would, each time you would pull it straight into a geodesic, and then you would find its reduced length, and you would count the reduced length of all those curves.
You have to fix a puncture.
Yes.
The mapping class group fix a puncture automatically.
So the curve, by setup, so I'm only looking at this basic case where curves, it's simple, starts out in infinity, comes in and goes back out. Certainly, the mapping class group acts on this. It's essentially a free homotopy class, and the mapping class group acts. So we can look at all these lengths. And it's for structural reasons, which I'm going to show you in her argument, her approach, why we expect this polynomial growth. In fact, why we always expect this polynomial growth.
Word after the number sign.
Right. Lariats. Oh, so I'm calling these lariats. This is my test of people's knowledge of the English language. So let me say something which will be some people's amusement. I've gotten more questions on this word from native English speakers.
Because we don't understand the rest of the word.
It's not a rare word, and such a rare word in the English language.
As non-native speakers, the non-native speakers are more comfortable with words we don't understand.
Well, the native speakers should know it, but it seems that's not the case.
It's a rare word of the 21st century.
Our president never says that word.
Maybe lots of foreigners learn English by watching old cowboy movies.
Yes. So one is, certainly in the West, people wear these string ties. Men wear these string ties, and that can be called a lariat. All right. So now I'd like to go through the outline of our argument, and certainly the first question, because certainly several very interesting quantities here, but the most obvious one we should be preoccupied here. The most obvious is, why are we even getting this polynomial growth? That's the most obvious question. All right, well, the answer is going to be, in fact, it's going to be straightforward. It's going to be because the basic reason is because we're counting integral lattice points in some Euclidean space. That's a slight oversimplification, but the following is correct. We're going to be counting integral lattice points in a space that's a integer PL manifold, and it's going to have whole regions that are certainly equivalent to an orthant, and in that orthant we're counting integral lattice points. And so the underlying reason is that there's a lattice, a Euclidean lattice, or something, essentially a Euclidean lattice in a Euclidean space underlying this question. And even in Riven's original result, he has this occurring, that there's a lattice in a Euclidean space.
Does that have to do with the line bundles?
No.
Moduli space?
No. It's going to be ML, measured laminations. It's going to be very much Thurston. All right. So her, and again, this is why at least I personally like her proof a lot, and that is there's a lot of players going on. I think of it as something like an opera with and you're at the final scene of an opera where multiple persons come onto the stage, multiple characters come on and perform all at the same time. All right.
I'm getting a little off. Can you remind me exactly what you're counting?
Number of, let's go back page 1. So I take a weighted multicurve, and I take its orbit under the mapping class group, and for each element in the orbit, I find its length, and then I'm counting how many of them have length less than L. And I'm going to do this as an asymptotic count, meaning I'm interested as L goes to infinity. What's the asymptotic of this? The proof has two main components to it. So the first one is, we have this counting function that I just described, and it's going to be integrated over the Riemann moduli space of Riemann surfaces with respect to Weil-Petersson volume. And so the first part of her approach is that she gives a recursive way for us to compute this completely as a polynomial. And in fact, the coefficients of it are going to be intersection numbers for the moduli space. So this is one, and her approach, I already said this is recursion. So this is one part of her approach. The other part has to do with the space of measured geodesic laminations. And it's going to be an explanation or elaboration of why this counting that we're looking at is, in fact, it's given by, on this space, which I'll describe, there's a natural measure and the Thurston measure. And in fact, this counting, once we do the scaling, this counting is just going to be given by the Thurston measure on ML or MGL. And then she's going to certainly bring these two pieces together. So first, I'd like to describe about the integral. So not about Thurston material. All right, so if I take the characteristic function of the interval 0 to L, then this counting of multicurves, I can just say it this way. So the mapping class group acting on the multicurve has a stabilizer, including Dane twist. And so to enumerate the orbit, then that's just going to be the quotient, a mapping class group by the stabilizer. And so if I take that quotient, then I'm going, well, so here, let's see. Oh, it's fine. So in here is also there should be a length in here. That is, I left that out, sorry. So it should be chi of length of h of r. All right. So that is, we take translates of the surface, and then for each one, we pull that multi-curve taut on that new surface. We find its length, and then we apply the characteristic function to see if it's in the designated interval. So this counting function can just be written this way. All right. Now, we're integrating this counting function over the moduli space relative to Weil-Petersson volume. And so this counting function is just the translates by this group quotient of a basic function. So I can do the standard move the sum, which I'll now describe. That is, this is summing translates of a function chi. I can do change of variables so that rather than translating my function chi, I translate the domain, so you could think of a fundamental domain. I translate the domain over which I'm integrating. So that just amounts to this. That is, I rewrite and that the sum acts on a fundamental domain, and then I end up with this. I end up integrating over Teichmüller space modulo the stabilizer and this characteristic function. All right. There's a finite symmetry group involved. Which I don't want to say more about. Which is not hard, but it's tedious. All right. All right. Now, we need... So her integration scheme depends on the fact that there's a very simple formula for Weil-Petersson volume. So let me describe that formula for Weil-Petersson volume. And it's that formula which enables her to do a recursion. So this is particularly important. All right, so to do this, I want to review for you a little about Fentanyl-Nielsen coordinates for Teichmüller space. So here's a way to think of Teichmüller space. It's the theorem of Fentanyl-Nielsen that you can build every Riemann surface from pairs of pants by varying the lengths of the boundaries. So when we attach two boundaries, they have to have the same length, but there's no restriction on that length. So you could vary what the length of the pair of boundaries is. And also, boundaries of pair of pants are geodesic boundaries. So the boundary of a pair of pants itself has an S1 symmetry. And so when you're attaching two pairs of pants, you're attaching two S1s. Well, there's a degree of freedom in making an identification between two S1s. And the degree of freedom certainly by the lift of the angle. And so there's the Fentanyl-Nielsen tau parameter, which I'm going to measure as follows. And that is, in each pair of pants, you can drop a perpendicular from one boundary to another. That gives you foot points on the boundary. Then Fentanyl-Nielsen's scheme is you just measure the displacement of foot points when you do the attachment. And you start off initially, I'm going to say by direct measurement, and then you prolong this, and we're actually in a simply connected space. So as you rotate around, you're following the continuation, the prolonged version of that measuring formula. All right. So the very nice thing about Weil-Petersson volume is the following, and that is it has a very simple formula in terms of these coordinates tau L, because in fact these coordinates tau L are global coordinates. They're global PQ coordinates for the symplectic form. There's a symplectic structure here, but we don't need that. We only need the volume form. So the short version of that is the following. The Weil-Petersson volume element is precisely this quantity. Yes, yes. Fine. So in a minute, we're going to be using this, sticking this in, because I have an integral up here. I'm going to stick this in for the volume element, and we're going to talk about the integral. All right, let's take an example case to see how this would go. And as I said, her integration schemes are recursion. So it's to take a surface of a given topological type and write this integral in terms of integrals of surfaces of smaller topological type. All right. So to be explicit, I'm going to take this case that we have, that this is our multicurve. It has two simple closed curves involved. And I'm going to just use this picture, and that is the multicurve breaks up the surface into two pieces.
The way you've written the volume form, you don't need the coefficient.
Okay, yeah. Well, there's always, yeah. So actually, I'm never straight in a way because there are two different ways to define the wedge product, and I always go back and forth which ones. Thank you. All right. Now, let's think for a moment what the stabilizer is here, because we know up here, in fact, it's sitting right here. We're going to have to take Teichmüller space modulo the stabilizer of the curve. All right, so what's the stabilizer of the curve? So, and that means the union here. So it's the union of these two curves. Well, the stabilizer of this curve, so it involves Dane twist around these two. That's easy. But there's a more interesting piece to the stabilizer. The stabilizer certainly includes the mapping class groups of R1 and R2. R1 being that we already cut off this surface R1, all right? And certainly every element in that mapping class group, because there's only one boundary, preserves the boundary. So our stab includes, in fact, the product of the mapping class group of R1 and the mapping class group of R2. So when we go back up here and take a quotient by the stabilizer, we're going to, in fact, take Teichmüller space and mod out by the mapping class group of R1, which is going to give us the moduli space of R1. And then we're going to take the mapping class group of R2, mod out by that on Teichmüller space. That's going to give us the moduli space of R2. And then we're also certainly going to mod out by the Dane twist. And I'll get to that in a minute because that's much easier. All right. So this integral, and remember, it was that we integrate up until we have length L for our multicurve. Here's our multicurve. So the effect of this characteristic function is that the length of this will be less than or equal to capital L. All right. So now you can actually say what the integral is. So the integral is as follows. It's when you quotient out by the mapping class group of R1, you get the moduli space of R1. So, a beautiful feature of this formula is that the product in the wedge product goes along with the attaching of pieces, so that the Weil-Petersson volume form for the whole thing is the product of the Weil-Petersson volume forms for the pieces. So that is as far as Weil-Petersson goes, that says we can reduce to smaller genus cases. All right, so we mod out by mapping class group R1. We just get the moduli space of R1. And R1 now being Riemann surface, which has geodesic boundary of length L1. And then we get the volume of the moduli space of surface R2, where the boundary of R2, so the boundary of R2 has three components, and one component has length L1, the other two components have length L2. So this is a polynomial in two variables. All right. And then All right, now we have the d tau. All right, so tau was measured in hyperbolic displacement, and we took stabilizer of those curves, so it has the Dane twist in the stabilizer. So we only need tau to vary through a fundamental domain for angles. That is, tau only needs to cover one rotation, a single rotation. And I'm measuring in displacement. And so in displacement, one rotation is where tau goes from 0 to L. That's it. So we know what the tau integral is, because tau integral is the integral, again, of d tau from 0 to L. All right, so we integrate the taus, and we just get this. For the integrand, we already integrated the Weil-Petersson volume forms for these lower genus surfaces. So this is her recursion formula. And that is this above integral. So this is a very nice result in its own, and she used it for other purposes also. The above integral that was up there is equal to the integral in just two variables of volume of this moduli space times volume of that moduli space times this simple factor here. All right. Now, it's a recursion. When you start the recursion, you see immediately the first term is a polynomial, and then we're just integrating. Oh, and sorry, this is the region I already explained that we're integrating over. All right. The first case of the recursion, you directly calculate, and you see it's a polynomial. Certainly then, looking how this integral's set up, all these integrals for all genera will be polynomials. Now, here's a part of the tale that I'm just going to tell you. I'm not going to explain because it involves yet a different sophisticated construction. So, in fact, it's not an accident that that integral was a polynomial. There's a lot of structure going on behind the scenes here. And in fact, this is a setup. It's already set up for symplectic reduction with Hamiltonians. And so that would be another way for us to know that these integrals are polynomials. And that tells us, knowing that it's symplectic reduction, tells us two more things. So it tells us ahead of time what the degree of the polynomial will be. We could have seen that by recursion, but symplectic reduction tells us this immediately. Oh, you might, so I'll say one thing, because people who have some familiarity ask, what's the symplectic space we're using? So we're considering Riemann surfaces with boundaries. We're considering that on the boundaries there's a marked point, and the S1 actions are that these points can rotate around the boundaries. And these are the, and the length squared of the boundary are the Hamiltonian functions. So when you do symplectic reduction, you also get the following, which feeds into the original statement, and that is you get that indeed this integral is given by characteristic numbers. And it's given by characteristic numbers of two of the very well-known characteristic classes for the moduli space of Riemann surfaces, the so-called psi classes. These correspond to the points going around the boundary. And the full polynomial also involves kappa 1, which is a so-called interior class for the moduli space. If we're just interested in doing the asymptotic that I'm speaking about, that the leading terms in the polynomials only involve characteristic numbers for psi classes. So, and part of what's going on here is she's giving a recursion for the intersection numbers of psi classes. And certainly there was a grand conjecture, which had already been settled, about the recursion for intersection numbers of psi classes, and that was Witten-Kontsevich conjecture. At the time that she did this work, it already had at least 2 proofs, and I believe that's the count, maybe 3. So this was not, because she has another paper where she gives a proof, independent proof of Witten-Kontsevich, but it was not, certainly, there were already at least 2 proofs in existence at that time already. All right, enough said about the integral. So now I went change to the, I'm going to say the second act of the opera, if you like. And this is going to be of how do we know this integral? Because the assertion is that this integral is a large part of the answer to her formula. How do we even know that? And what are we, what's even the context for that? All right, so this, I'm going to now describe a little about measured laminations. And let me start there and then tell you some basic facts and certainly some very nice other theorems about measured laminations. So first, keep in mind, in the back of your mind, that on a hyperbolic surface, when you have geodesics, they intersect the minimal number of times as allowed by their homotopy classes. So when we're looking at geodesics on a surface, looking at their intersections is in fact a topological piece of data. That is the number of intersections. And, well, looking at the number of intersections, topological information. By thinking about very long, simple geodesics and what they look like, Thurston came to the following point of view. So let's start here. So if we have multicurves, and we want to actually think that these multicurves, and say we want to think that they're a dense set in some space, and something that's at least topologically equivalent to Euclidean space. So certainly what we need, or certainly the bottom line or key matter is, well, what would be the topology you would put on the set of multicurves so that they become a dense set in anything? So the following Thurston, the topology is the following, and that is when you have a simple closed geodesic, then you can consider its intersection with a multicurve. And so our multicurves are weighted. So what that means is the following. You add up with the weights, and weights are always non-negative. So you add up with the weights, the actual geometric intersection number of your test curve against the components of your multicurve. All right, and this gives you an intersection number. This is a functional. So you have a set of points. We have and we get one functional for every simple closed geodesic. We have a set of points. We have an infinite collection of functionals. We can make the completion of the space relative to those functionals. All right. So that's one description. In some sense, it's not the most geometric, but it's certainly the fastest. So this is a description of Thurston's space MGL, measured geodesic laminations. All right. What are the properties of MGL? Because we're going to be working with MGL. So first off, MGL, the way I've done it, I've used geodesics. So that requires having a hyperbolic metric. Well, in fact, there's a description. This is not surprising because remember, geodesics only intersect if they are forced to by their topology. And we're looking at counting intersections. So presumably or reasonably, we could somehow count intersections without having a hyperbolic metric. And in fact, that's correct. There's a characterization of MGL without introducing a hyperbolic surface. As a matter of efficiency, I'm not going to say what it is, but it's in fact very geometric, but it involves several constructions. All right, the mapping class group acts on this. And it acts on this because certainly mapping class group acts on simple closed curves on a surface, so it acts on this space. And the intersection numbers preserved by the action of the mapping class group. All right, so the key facts, here are some key facts. So it's a PL manifold, piecewise linear, and it has this dimension. And it has very nice linear charts, which come from train tracks. And what's useful for us, or very important, is that it has a natural volume form. And we're going to see, there are two descriptions of this volume form. We're going to see one of them. The original one is in terms of train tracks. We're actually going to see one in terms of lattice points. All right. Then there's this beautiful theorem of Mazur. So, in fact, people, there's been a lot of work on the mapping class group, a lot of work on MGL, a lot of work on mapping class group acting on MGL. All right. So, and there are many very nice theorems there. So one of the very nice theorems there is if we consider well, first of all, I should have said it here. This Thurston measure is invariant under the mapping class group, first of all. All right. So this very nice theorem of Mazur is that the Thurston measure is ergodic with respect to the mapping class group. So any invariant set by the mapping class group either has full volume or zero volume. All right. And this is going to be very useful for us. So now it's time to say what this unit ball is, which was back on the first page. So the unit ball is so I should say this. This length function, when you take the length of a multicurve by adding up the weighted lengths of the components, this length function extends to be continuous on MGL. Fine. So this BR ball that was back on the first slide, this is just the elements of MGL whose lengths at most 1. So it's the ball of elements. It's the unit ball relative to this function. That's all it is. All right. Now, with that said, let me proceed. So in MGL, a natural subset are the multicurves which have integer weights. And it's very nice, so I'll say background, that the ones that have integer weights, these multicurves, these are exactly, in fact, the elements of MGL which in Thurston's train track parameterization have integer weights on the train track. They're exactly those elements of MGL. So this is a intrinsically defined set, and it's a natural set. All right. Now, this is my last page, and this is the going to be the finale, I'm going to say, of the opera. So we're going to define two measures. So one that's, let's start here. One that's immediate and obvious, and that is, I have this set, I have MGL, I have this set of multicurves that have integer weights. While another operation that we have on MGL is dilation. That is, you can multiply the weights of a multicurve by any positive real number. And this extends to be continuous action on MGL. So we have this lattice-like subset, that is the multicurves with integer weights. Well, we can define a measure from that. How do we do that? We're going to scale that lattice-like subset. We're going to scale it towards the origin, and then it's going to become more and more dense. And what we're going to do is, down here, take the limit of given an open convex set, we're going to count how many points of the scaled lattice are in our open convex set, and we'll just take the limit. So this is certainly one of the characterizations of Euclidean measure. Now, with us doing that, we could also actually do this with our multicurve. And that is, we have our multicurve. It has an orbit inside of MGL by the mapping class group. So it's some sub-lattice-ish set inside a lattice. At the moment, we don't know how regular it is. It might have big islands and yet clumps of mass. So that we don't know, but we know it's at least a sub, well, in a minute we'll know it's a sublattice of the integer lattice, or we can think of it that way. But we'll do this same operation. That is, we'll scale this set, given an open convex set U, we'll scale this set to shrink it more and more, and we'll count how many points of the shrunk set are in a given open convex set, and then we'll take the limit, or at least a limit on a subsequence, and this will define a measure. All right. Now, by the way we've set it up, both of these measures are mapping class group invariant. The multicurves with integer weights are obviously mapping class group invariant subset. And this was an orbit. So this, whatever limit we get here, it's mapping class group invariant, just by the way we set it up. All right. The scaling of the lattice itself goes to Thurston's measure. And at this point, in this argument, we could just take this as a definition of Thurston's measure. All right. Now, I said at the beginning, and this is for convenience, the multicurve we're looking at had rational weights. So I'm going to multiply it by an integer to clear the denominators. And then once I clear the denominators, so I'm multiplying the multicurve, it now has integer weights. So it's now a subset of the integer lattice. So then when I count how many points are in that set, except for this scaling factor, whatever the count is, it'll be dominated by counting how many points are in the full lattice. So now I take a sequence, at least, of L's to ensure that I get convergence, because I don't want to take a limit along a sequence. All right. So I take a limit along a sequence. And then what do I have? As I already explained, the limit, even before I took the limit, it was mapping class group invariant. The limit's mapping class group invariant. And also, in this construction I already described, I'm only using the topological description of ML. So, first of all, when I take this limit, whatever I'm getting, it does not depend on a choice of a Riemann surface. It only depends on topological information. All right, now's when I invoke Mazur's theorem. And that is, since this is dominated by this, when I take its limit, it's dominated in the limit. That is, the limiting measure, for this one. The limiting measure here is going to be absolutely continuous with respect to this limiting measure. This limiting measure is ergodic. So, in fact, the limiting measure I get along my sequence will be just a multiple of Thurston's measure because of the ergodicity. So the ergodicity is beautiful and really convenient at this point because it nails down, it says the limit has to be precisely this type. All right. Now, then Mariam, once again from here, just does something very astute. And that is, we have this limit. It only depends on topology. But at the same time, we have an unknown constant in here. So Mariam just says the following. Well, we have unknown constant. It only depends on the topology. Let's integrate both sides over the moduli space, and we'll get a formula for that unknown constant. So that's, in fact, I'll just describe. That's the last step. But let me remind you where we are. So this mu L over gamma, this measure, this is just counting how many multicurves have length less than L. That's just our original counting function over L to the power. So this is the counting that we're interested in the whole time. All right, we already have it's going to unknown constant times Thurston mass of the ball. All right, so now she integrates over the moduli space, and this is it. And how's it? Because here's our unknown constant. This was just one of the quantities in her final formula. This, I described to you how you compute it by this recursion. So this is in our final formula. This we compute. That tells us what the unknown constant is. That's it. And going back, remember what's sitting here, and that is unknown constant times Thurston volume of ball. This is just the limit of our count. I'll stop here.
So what if the coefficient of multicurve is real?
So the coefficient is, so it involves these weights, first of all, in the multicurve. And then it is part of the symplectic reduction that this involves. So it's the top wedge of psi classes. So in fact, it's the sum of the top wedges of psi classes. So these are these standard characteristic classes. And so, and you put in one psi class for each boundary that you're working with, because this was a recursion. So at a given stage, we have some boundary there. And so when we're evaluating that integral, then we have a boundary of the Riemann surface. Well, then you imagine you could take that boundary, replace it by a cusp, and then there's a psi class for that cusp. And so we're using that psi class. So there are these psi classes each time we do this recursion, and you only, in fact, because she gives the full polynomial here, but for this argument, we're only interested in the leading coefficient. And so the leading coefficient just comes from all the possible wedgings of products of psi classes for the boundaries that you're working on in your pictures. Yes?
Could you say a few words about the finite symmetries of the
Yeah. So if you have a finite symmetry, then because throughout this argument, I'm really using that, as I've written it down, that curves are labeled. Even here when I wrote 1 and 2, that is, curves are being labeled. So the symmetry might permute the elements of the multicurve, and then that would move the labels around. So then you realize, oh, you would be overcounting. If you have a symmetry, then you'd be overcounting. But the symmetry at this point would be for the weighted multicurve. So if you have a symmetry, the weighted multicurve, if you just were literally doing what I have written here, you'd be overcounting by a factor of the symmetry itself. It turns out in practice, these are more involved than one thinks, because you can, once you start, actually, I'm going to say looking through, there are various special cases with symmetries for curves or Riemann surfaces, and in actual practice, it's a little bit of a headache, but you know what the description of it is that you're looking for, but to actually count it takes some more care. Yes?
Are there some results for discounting where we fix L and change the genus?
Oh. So, certainly broadly speaking, yes, because I'm going to say the following, and that is these formulas that Merriam had certainly one of the themes she pursued, because this is very early work for her. In the later work, she was certainly pursuing the genus asymptotics of various of her formula. So certainly, broadly speaking, yes. Here, actually, the answer is yes here, too. I was just thinking, because certainly in algebraic geometry, one's interested in the asymptotics of what these intersection numbers are, too. So the answer... It turns out, I mean, at least the one she looked at, she looked at with Peter Zogroff, it turned out to be a rather tricky question, because the recursion, if you just take it as it's sitting here, it's a rather long recursion and not very tractable. So to actually get tractable expressions, to actually write down asymptotics, took some real work, even in the case, say, of volumes.
Listen to the speaker again.